These are Calculus Notes 14.1, the start of Chapter 14. Differential equations is what we'll be covering in Chapter 14. So let's get a brief summary of what we're talking about there. First of all, a derivative. A derivative is a rate, a slope, a rate of change. A differential equation, then, is an equation that has at least one derivative in it. We have some examples here. You can see that y prime equals this equation. Y prime equals this equation. And in this one, we even have another derivative in there. The third derivative of y. As you recall, we can write a derivative using the dy dx nomenclature. So this is also a differential equation because it has a derivative in it. And then finally, we have y, the second derivative of y equals another y. Any combination of this that has at least one derivative in it is called a differential equation. The order of a differential equation refers to the highest derivative. Same idea as up above, the order of the polynomial is the highest degree of the exponent. The order of a differential equation, emphasis on differential, the derivative, is the highest derivative in the equation. So you can see that in this example, we have y prime, or the first derivative of y. Therefore, this is a first order differential equation. In the next one, we have a y prime, but we also have a y double prime, or a second derivative. Therefore, this is a second order differential equation. Just like the polynomial above does have a x to the first power, but it has an x to the second power, so this is of degree 2 in our polynomial. So same idea with our derivatives. If this was a third, it'd be a third order. Now, a solution to a differential equation is usually not a number. We're kind of used to solving things and getting a number, but a differential equations usually is not going to be a single value. It's going to be a function, or sometimes even a relation. You can recall back Algebra 1, how a function and a relation are related, but can be something totally different. So what we're going to do here to find our solution is find that function or relation that makes the differential equation true. Just like a solution to a polynomial, some equation might be the set of numbers that make that true. This will be a function or a relation that will make that true. So let's take a look at this differential equation. It's a differential equation because it has a derivative in it. Matter of fact, it's the second derivative of y. And we're given 1, 2, 3, 4 different equations. We're going to look at each one individually and answer this question: is the given function a solution to this differential equation? So let's start off with this one. Well, in this differential equation, we need our second derivative. So let's find that second derivative. Obviously, that goes through the first derivative. Derivative of sine is cosine of x. So the second derivative is going to be negative sine of x, or the opposite of sine of x. Let's check and see if that makes this true. Y double prime would be negative, or the opposite of sine of x. Y is sine of x. Does that give us 0? No, it does not. So this does not make that differential equation true, so it is not a solution. Let's try our next guy. First, let's find y prime again. We've got chain rule here. Derivative of e to the x is e to the x, and then derivative of the inside would give us 2. Our second derivative would be the derivative of this, e to the 2x Derivative of the outside, keep the inside, times the derivative of the inside is going to be another 2, times this 2 would give us 4e to the x. Let's substitute these in. First, we'll have 4e to the 2x, and then we'll subtract 2e to the 2x. Does that equal 0? Obviously not. 2, or in this case, I substituted the wrong thing in here. Sorry about that. This was supposed to be just e to the x. Sorry about that. It still doesn't make any difference. 4x minus, or 4e to the 2x minus e to the 2x gives us 3e to the 2x, which is not equal to 0. Let's try our next one. In this one, y prime would be 4 times the derivative of this. Well, in this case, we have again chain rule, which is going to make this a negative 4e to the negative x. Take the derivative of that. Chain rule comes into effect again. So this negative 4e to the negative x becomes a positive 4e to the negative x. Let's substitute these two things in here. This time I'll try not to mess up. So our second derivative is 4e to the negative x. We're subtracting the original function y equals 4e to the negative x. Does that equal 0? Yes, this time it does. So this one is a solution. Y equals 4e to the negative x is a solution to this differential equation. Let's try our next one. This is some constant c times e to the x. First derivative will give us c times e to the x. Second derivative kind of looks exactly the same, c e to the x. Let's substitute and check. Our second derivative is c e to the x. Subtract the original function, c e to the x. Does that equal 0? Yes, it does. So this one is also a solution. Okay. We've got a new differential equation, and that's represented by this. And some more equations to check on it. Second derivative of y plus 2 times the first derivative of y plus y equals 0. So let's take a look at this guy here. Again, we'll need to find second derivative. We also need the first derivative this time. This will be e to the t. Second derivative is e to the t. So a little bit boring here, but let's just substitute those in and see. Second derivative, e to the t, plus 2 times our first derivative, e to the t, plus the original function, e to the t. Does that equal 0? Well, obviously not. This is going to be a 4e to the t, which does not equal 0, so not a solution. Let's try our next one. This time, y prime is going to be e to the negative t. Well, it's going to be negative because of our chain rule. Our second derivative, using that chain rule, will change this negative back to positive. Substitute those in. We'll have e to the negative t. And then we're going to add 2 times our first derivative, which actually is going to give us the negative 2 e to the negative t. And then add y, which was e to the negative t. Does that equal 0? Yes, it does. So, yes, y equals e to the negative t is a solution. Let's look at another differential equation. And the next one says, show that, important words here, especially when we're talking about AP language, show that. Show that means that think of this as prove start with something, get all the way down to a conclusion. So with show, we want to make sure we start with something and end up with what they're asking us to prove. So in this case, it says show for any constant c, this function is a general solution to the differential equation y prime equals x times y. So in order to show this, we can do it two different ways. We can either start with this one, or we can start with this one. If we start with the y equals c e to the 1/2 x squared, we're going to end up with our manipulating down to this. If we start with this one, we're going to have to manipulate and show a path to this one. So I'll go ahead and show that both ways. So first of all, if we have y equals c times e to the 1/2 x squared, and we take the derivative of that, y prime would be constant times, chain rule here, derivative of the outside is e to the x, keep the inside, 1/2 x squared, times the derivative of the inside. What's the derivative of the inside? The derivative of the inside will be derivative of x squared is 2x, 2x times 1/2 is x, so y prime equals x, or excuse me, let me rearrange this just a little bit, sorry, c times x, or wait a second here, I want to show this right here. So I'm just going to move the x out in front so that it's x times c e to the 1/2 times x squared. This term here is what y is. So we can substitute in y for that and show that y prime equals x times y. Let's go with this other one. Let's start out with y prime equals x times y. Well, we over here found y prime. We can substitute in y prime into this equation, and that'll give us c times x times e to the 1/2 times x squared, and that equals x times y. If we divide both sides by x, this leaves us with c times e to the 1/2 x squared equals y, which was this right here. Okay? So in both of these instances, I want to point out, we're starting with one, doing some type of algebra, derivative, manipulation that gets us to the other. And that's what we're trying to do when it asks us to show that. Next one says, let's find a solution to the differential equation y prime equals y. Now, if I were in front of you, I would be calling on a few of you to answer this one. I know some of you already have an answer to this one, and yep, I heard that. That's a good response. Yes, oh, I heard that one too. Very good, very good. Nice try. Let's think about another one. Good job. That's an interesting one. Did anybody else think of that one? Very good. Now, of course, I know what you guys were saying. You were saying, hey, what about y equals e to the x? Because the derivative of that is just e to the x. So y equals y prime. And of course, that's when Caitlin said, well, what about y equals 2 times e to the x? Because the derivative of that was 2 times e to the x. which of course is the same thing, so y equals y prime there. And, of course, Sean was trying to be fun, and he said, well, what about y equals 0? Because the derivative of that is still 0, which means y equals y prime. And then I did hear several of you talking about maybe even going crazy and doing something like -3 e to the x, which would give us y prime is -3 to the x, so y equals y prime for that one. And in reality, most of you realize that, hey, if we take any constant times e to the x, the derivative is always going to be that constant times e to the x. So the general solution to y prime equals y is y equals c times e to the x, where c represents any constant. Now, usually a differential equation will have infinitely many solutions. Obviously, we can use 1, 2, 3, 4, 5, -2, 0.375, all of those for c, and you can see why this general solution would have infinitely many solutions. Each differential equation then has a family of solutions. The family of solutions includes that constant c. But if a differential equation has an initial value, some type of ordered pair, then the differential equation will have only one solution. And we've done that before with some other equations. Remember our velocities and distances, where if we were given that initial value, we could come up with that equation for dy dx, kind of the same thing here. So we're going to concentrate now on solving these. Solving differential equations can be done two ways. One is by using antiderivatives. And then the other one is by something called separation of variables. We are just going to do antiderivatives now. Okay? So in this example, it says if y prime of x equals 2x minus 3, let's find y if y of 1 equals 4. So given that y prime of x equals 2x minus 3, we can integrate this. The integral of y prime with respect to x is just going to give you y, or y of x. Slide that in there. So if we integrate both sides with respect to x, we'll get the equation for y. Antiderivative of 2x, of course, is x squared. Antiderivative of -3 is -3x. And don't forget our little buddy c, because that's going to give us the specific solution. When we substitute in 1 for x, we should get 4. So what's this going to give us? This will say 4 equals 1 squared minus 3 times 1 plus c. 4 equals 1 minus 3, or -2. Add 2 to both sides, and we get c equals 6. So find y. Y equals x squared minus 3x plus 6, the value we found for c. Next, we'll take a look at this function. This time, we're going to find a solution that satisfies both this differential equation, has a y prime in it, and the initial condition y of 0 equals 1. So, do the same thing we did before. Y prime of x, integrate 2x, x squared plus 1 dx. Remember back to our days of integration here. This looks like a u substitution to me. Let's let u equal x squared plus 1. Du will be 2x dx, which is pretty nice, which means this is just going to be the integral of 1 over u du, which is the natural log of the absolute value of u plus c. Don't forget our plus c. Plus c has to appear at the very first spot. Okay. Then we can substitute back in u, the natural log of the absolute value of x squared plus 1 plus c. And of course over here, this just equals y. When we substitute in 0 for x, we should get 1. So let's find out what c is given this. 1 equals the natural log of the absolute value of 0 plus 1. Well, oh, and plus c, sorry about that. 1 plus 0 is 1. Natural log of 1 is 0. So in this case, c equals 1. And we get the function y equals the natural log of the absolute value of x squared plus 1 plus, oops, sorry about that, plus 1, the c, will be the function that satisfies this differential equation and this initial condition. Let's attack our next one. We've got initial conditions, and so back this time we have two sets of initial conditions. And this time we have a second derivative. So let's integrate y double prime and 2 minus 2x with respect to x, or excuse me, 2 minus 6x. This will give us y prime equals 2x minus 3x squared plus c. Now I'm going to put a c1 in here this time because I know looking ahead I'm going to have to get another antiderivative and another c, so I'm not confused with this one. We'll use these initial conditions, which means 1 equals 2 times 0, 3 times 0 squared, which of course is 0, so c1 equals 1, and we have the equation y prime equals 2x minus 3x squared plus 1. Let's go again. We're going to go all the way down to the actual function. So we're going to integrate this again with respect to x. This will give us y equals antiderivative of 2x, x squared. This will be x cubed multiplied by the reciprocal. That'll give us 1/3 of 3, which is 1. And then plus x plus our second constant, c2. This time, we'll use these initial conditions, which says 4 equals 0 minus 0 plus 0, or c2 equals 4. I'm sorry, I really messed up, didn't I? I just noticed that. I've got things switched around, which is not so bad for me to fix. You can see that I've got my initial conditions switched around. This one should be 4. Y prime of 0 equals 4, which would change this to 4. And then my second initial condition should be down here. So when I have this, we should have had x squared minus x cubed plus 4x plus c2. When we substitute in x equals 0, 0, 0, 0, but this shouldn't equal 4, this should equal 1. Sorry about that. I know some of you were yelling and screaming at me while I was doing it, and I couldn't hear you, but I'll listen next time to you. So now that we know that, we get our final equation, y equals, and probably most of you will switch it around so it is in proper order here. This will be a negative in front of the x cubed, and then plus x squared. This, recall, when I fixed it, was a 4x, and then this guy here, 1. That is the solution to our differential equation. Next, let's find a solution that satisfies the differential equation, this, given these initial conditions. Well, we know that y prime equals y will be of the form y equals c times e to the x, because that's the solution, or excuse me, that's the differential equation that we showed on the previous page is solved when y equals some constant times e to the x. Which means, if we use these initial conditions, that'll mean -1 will equal c times e to the 0 power. So c equals -1, and y equals -1 times e to the x. That is the function that satisfies that one given these initial conditions. Our next one gives us a differential equation of ds dt, which could have been s prime, just like up here. This could have been dy dx, our second derivative with respect to x, dy dx up there. This is no different. It's still a differential equation because that has the derivative in it. We have this initial condition, so we will go ahead and integrate this s prime of t with respect to t. I guess I should put my dt in there, is going to be the integral of 12t times 3t squared minus 1 all cubed with respect to t. I think let's go ahead and do some more substitution, because I don't see us foiling this out and then multiplying by 12t. It looks a little messy. So let's just attack this, and let's set u equal to 3t squared minus 1. du then would equal 6t dt, which means if we want 12t dt, 2 du would equal 12t dt, and that'll take care of these two guys here, with this being u. So substituting, this will be 2. I'll put that in front of my integral so it doesn't mess me up or get in my way. U cubed du. Of course, this will be s. So derivative, or excuse me, antiderivative of this will be u to the 4th multiply 2 times the reciprocal of 1/4, or excuse me, reciprocal of 4, which is 1/4, and 1/4 of 2 gives us 1/2 plus our buddy c. Then we'll substitute back in our u. S equals 1/2 times the quantity of 3 squared, or 3t squared minus 1 plus c. Our initial condition will give us 3 equals 1/2 3t squared minus 1, that quantity, plus c. Okay. Oops, I forgot to put in my 1 here. This is 1 squared. 1 squared, of course, is 1. And then, what am I going to do with that? I've got to multiply that by 3. 3 times 1, of course, is 3, minus 1 should give me just 2. 1/2 of 2 gives me 1. So this should be 3 equals 1 plus c. Next, what I'll do is I'll subtract 1 from both sides, and c equals 2, which means our differential equation, or the solution to this differential equation, will be s equals 1/2 times 3t squared minus 1 plus 2. Next thing I want to note here is at the very end. Okay? Told you there were two ways of solving differential equations. First one, which we just did, was using antiderivatives. And that's going to work sometime. It's going to work on your homework tonight. But it's not going to work all the time. Sometimes we may have to use something called a separation of variables. That's going to work sometimes. We're going to have to be proficient in both of these during the unit. But for now, let's get experts in using antiderivatives to solve differential equations. Enjoy your homework. I'll see you later.